Let us start. Now, let us discuss today the humidification and dehumidification. In addition to moisture to the air without change in its dry bulb temperature is known as humidification. So, similarly, the removal of moisture from the air without changing its dry bulb temperature is defined as dehumidification. So, humidification means we are keeping the temperature of your vapor air mixture and unchanged, and either you are adding vapor without changing the temperature, or as well as removing the vapor without changing temperature. This means the dry bulb temperature or actual when the temperature of the dry air when there is suppose there is no such moisture presence. So both this process, humidification and dehumidification, we are temperature of the original air mixture is supposed not to change, but we have to add the moisture as well as remove the moisture as per requirement. The heat added during the dehumidification process and heat removed during the dehumidification process is shown on the cyclogeometry chart. The temperature is not varying, but question is the heat is adding or heat is removed. Here, temperature is not changing, but heat is added, either added or removed. Or removed. Now, it can be noted that the relative humidity increases from phi1 to phi2. Means relative humidity means the amount of moisture presence, ratio of the amount of moisture actually present to the amount of moisture which is supposed to be present when the air is completely saturated. So if we add the moisture, the relative humidity will go up, and if we remove the moisture, the relative humidity will go down. So just one second. হ্যালো, হ্যাঁ বলছি যে 7 সেমিস্টার ক্লাস তো নেওয়াই যাবে এখন, কোনো অসুবিধা তো নেই। হ্যাঁ আমি নিচ্ছি, হ্যাঁ বলো। 2 to 3 দেখলাম, তাই আমার তো পুরো এই মেসেজ এসছে এতক্ষণে। ঠিক আছে। The heat added during dehumidification, a process and heat removed during the dehumidification process is shown on the psychometric chart here. Now, the relative humidity will increase as heat is being moisture is being added. Relative humidity is supposed to increase from phi1 to phi2, which is shown here. This is the relative humidity line here, and phi2 is the relative humidity line here. Phi2 is higher than phi1. So, in case of humidification, the relative humidity is supposed to increase, and specific humidity from the chart is shown that means humidity per kg of the dry air is supposed to be increased from W1 to W2. Similarly, in case of dehumidification, relative humidity will reduce from phi1 to phi2, and specific humidity also reduced from W1 to W2. So phi1 to phi2 and W1 to W2. Specific it is the mass. So if you add the moisture to your certain volume of your volume of the air vapor mixture, the relative humidity as well as specific humidity both will increase, and if you remove the moisture, it will both will reduce. Both this relative humidity and specific humidity will reduce as per your requirement. Just a second. Just a second. Now, it's supposed to be noted that in humidification, the change in enthalpy is shown by the intercept of H1 and H2 on the psychometric chart. So change in enthalpy will be the difference between H1 and H2 here, or H2, H1 minus H2 here for dehumidification. So the drive-up temperature of air during the humidification will remains constant. Therefore, its sensible heat also remains constant. Thus, it is thus obvious that the change in enthalpy per kg of dry air due to increased moisture content equal to W2 minus W1 per kg of dry air is considered to cause a latent heat. So what is clear? From the due to humidification, enthalpy is increasing and drive-up temperature of air during the humidification remains constant. So its sensible heat also remains constant. But temperature is not changing, only the latent heat is being added. That temperature, only latent heat is being added, not the sensible heat, as temperature is not changing. Thus, the change in enthalpy per kg of dry air due to increased moisture content equal to W2 to W1 kg per kg of dry air is considered to become a latent heat transfer. So here, this humidification basic is the temperature is not changing, so there is no sensible heat is being added or subtracted. So thus, total is subtracted. Thus, the total heat is being added or subtracted as per as in the form of latent heat only. So latent heat will be H1 minus H2, HFG, the latent heat of moisture multiplied by the W2 minus W1. W2 is the amount of specific humidity at after the heat moisture is added, and W1 is specific humidity before the heat is moisture is added. Please amount of moisture present per kg of dry air. Heat multiplied by the latent heat is the total amount of heat added as latent heat, where HFG is the latent heat of vaporization at dry bulk temperature. Now, for humidification, the above equation may be written as H1, H2 minus H2, H1, W1 minus W2. So here, H1 is enthalpy at the beginning, and if the heat is removed, enthalpy is reduced to H2. HFG is the relative enthalpy, and W1 is the moisture present before the dehumidification, and W2 moisture present after the humidification. So absolute humidification and dehumidification process are rarely found in practice. They are always accompanied by heating or cooling process. But in air conditioning, the latent heat per unit, latent heat load per minute is given as a latent heat mass of the air multiplied by the rise in enthalpy, mass of the air multiplied by the latent heat of latent heat by the enthalpy multiplied by the rise in water vapor and rise in the content of water vapor, or rate of air flowing in multiplied the density of the moisture, and latent heat vaporization, which is vaporization, is around 2500 kilojoule per kg, and WF, difference in the specific humidity between the entering and leaving condition of air. W2 minus W1 for humidification and W1 minus W2 for humidification. This substituting all these numerical values in the expression, it will become and the rate of airflow remains unchanged. 1.2 is the density of the airflow, 25 the latent vaporization multiplied by uh, change in specific humidity. So this will become 3,000 into rho into mu into W delta W, or theta into delta W into delta W divided by 60 and kilojoule per minute divided by 16 kilojoule per second. This will become reduced to 50 into V into WT kilojoule per second or kilowatt. So thus latent heat, which is added or subtracted, is supposed to be W50 multiplied by the rate of airflow, and multiplied by the loss or rise in the specific enthalpy. The humidification is achieved either by supplying or spraying steam. Now, what is the method of obtaining humidification and dehumidification? Now, the humidification can be achieved either by supplying or spraying steam or hot air, hot or cold air into the air. So we have to spray, or you have to supply either supply or you have to spray steam or hot water or cold water into the air. This humidification may be obtained by following two methods: direct method and indirect method. In this direct method, water is sprayed in a highly atomized state into the room to be air conditioned. This method is called humidification, is not very effective. Our indirect method, the water is introduced into the air in the air conditioning plant with the help of a air washer, as in figure here. They are conditioned. This conditioned air is then supplied to the room to be air conditioned. So the water has to be introduced first, water or moisture into the air with the help of a air washer. This conditioned air is then supplied to the room to be air conditioned. The air washer ventilation may accompany the following three ways. First, what we have here is a tank here full, and it's a pump under the tank, which is pumping the air from the tank, from the bottom of the tank, and then spraying the air through the top of the tank into the tank itself. So there is a continuous movement of air supply from bottom, heating goes through the heating or cooling medium as per our requirement. Then either hot or cold air goes up and spray from the top to the top of the tank. And we have, so what we are doing, we are maintaining a certain flow of water and a certain amount of water present in the tank and backed by a backup water if necessary. Then we are pumping it through the heating and cooling unit, then going up as a heated hot water or cold water and sprayed from the top. And air is introduced from the left side through a elemental plate and goes out and passes through the tank and absorbs the moisture and goes out from the right side of the tank. So it can be accomplished by maybe by the following three ways: by using air circulated spray water without prior heating of air, and preheating the air and then washing it with water circulated water, and by using heated spray water. In using recirculated spray water without air prior heating of air, by prior heating the air and then washing it with recirculated water, then be using located heated spray water. So how? First, you have to recirculate spray water without prior heating, air, or then by preheating the air, then wash it with recirculated air and use heated spray water. Here we can use heated spray water. Here we may not recirculate. We use recirculated spray water, but without heating of the air. That's also create moisture. Preheating of the air, then washing it with the recirculated water, then it absorb moisture, then totally by heating by spray water. So either you have to then you have to recirculate the spray water and without any heating or subtracting any of them. Then we'll preheat the heat air and then wash it through recirculated water without heating it. Then you use the normal temperature air and use the heated spray water through to make it vaporized, to improve its vapor content. The humidification may be accomplished with the help of air washer or by using chemicals. In the air washer system, the outside or entering air is cooled below its dew point temperature so that it loses moisture by condensation. The moisture removal is also accomplished with the spray water is chilled. When the spray water is chilled water and its temperature is lower than the dew point temperature of the entering air. Is they are leaving the air washer is it has its drive-out temperature much below the desired temperature room. Therefore, heating coil is placed under the air washer. The dehumidification may also be achieved by using chemicals which have the capacity to absorb moisture in them. Two types of chemicals known as absorbent, as carbon chloride and absorbent, and are generally used for this purpose. The dehumidification can be accomplished with the help of air washer or by using some chemical. In the air washer system, the outside or entering air is cooled below its dew point so that it loses moisture by condensation. The moisture removal is also accomplished in the spray water. When the spray water is chilled water and the temperature is lower than the dew point temperature, since the air leaving the air washer has its drive-out temperature much lower than desired temperature, therefore the heating coil is placed under the air washer. A heating coil placed under the washer and dehumidification is also achieved by using chemicals. Two types of chemicals known as absorbents and absorbents are commonly used for this purpose. As a matter of fact, they are heat added during a cyclomatic process may be split up into the sensible heat and latent heat. The heat added during a cyclomatic process may be split up into sensible heat and latent heat. Now, the ratio of the sensible heat to the total heat known as sensible heat factor or SFF or sensibility ratio known as SFR. Mathematical sensibility by total heat, sensible heat to sensible to latent heat, or where SH is the sensible heat and LH is the latent heat. The sensible heat factor also known as the right-hand side of the cyclomatic chart. So, what is the sensible heat factor? The heat added can be divided into sensible plus latent heat. The ratio of the sensible heat to the latent heat is known as sensible heat factor or sensible heat ratio. SFH is sensible heat divided by total heat, SH divided by SH by LH. SH sensible heat divided by LH sensible heat latent heat. The latent sensible heat factor scale, also known as the right-hand side of the psychometric chart. Then what is the cooling and dehumidification? This process is generally used in summer air conditioning to cool and dehumidify the air. The air is passed over a cooling coil or through a cold water spray. In this process, the dry bulb temperature as well as the specific humidity of the air decreases. This process is generally used in the summer air conditioning to cool and dehumidify the air. The air is passed over a cooling coil or through a cold water spray. In this process, the dry bulb temperature as well as specific bulb humidity of the air decreases. The final relative humidity of the air is generally higher than that of the entering air. The dehumidification of the air is only possible when the effective surface temperature of cooling coil is less than the default temperature of the air, that is equal to TDP1. The effective surface temperature of the coil is known as apparent dew point, and the cooling and humidity process is given in the figure below. Hello? Yeah. Check it. Now, what I have just told you, the cooling and humidity is generally used in summer air conditioning to cool humidify the air in a certain room or certain space. The air passes over a cooling coil or through a cold water stream. So we have to cool the water air if you want to pass it through the cooling coil or cold or spray. In this process, the dry bulb temperature as well as specific humidity of the air decreases. So the specific heat, it is reduces to a certain extent, and specific humidity, the amount of moisture present is also reduces to a certain extent, means the air vapor air mixture becomes a bit dry instead. The final relative humidity of the air is generally higher than that of the entering air. Now, it's generally higher than the entering air. The humidity of the air is also possible when the humidification is also possible when the effective surface temperature of the cooling coil is less than the dew point temperature of the air passing through the coil. The effective surface temperature of the coil is apparent dew point and effective ADP, and the cooling and humidification is shown in the figure as we. Now, say TD1 is the dry bulb temperature of the air entering the coil. You plot it here as well as here, dry bulb temperature both sides. TDP21, dew point temperature the entering air, TDP1, and TD4, effective temperature, surface temperature, or effective dew point temperature or of the coil, that is TP1. TD4 here, and it is also TD4 here. Under ideal condition, the dry bulb temperature of the air leaving the cooling coil should be equal to the surface temperature of the cooling coil. Dry bulb temperature of the air leaving the cooling coil is supposed to be equal to the surface temperature of the cooling coil, but is never possible due to the efficiency of the cooling coil. Therefore, the resultant condition coming out of the coil is shown by point 2 in the straight line joining with 1 to 4. Now, here H1, we got the point W1 and TD1 here, specific humidity as well as the dry bulb temperature, and TD4 is a specific humidity here. And if we join it and we see that TD4 is always air would be equal to TD4, but it never happens, it becomes TD2. So the idea that is not possible, therefore the resulting condition of air coming out of the coil is shown by a point 2 on the straight line joining 1 to 4. The bypass factor in the oil case is given as bypass factor TD2 minus TD4, TD2 minus TD4. It is component of the incoming air, the terms of the air leaving the humidity pressure plus minus the temperature of the cooling coil minus temperature of the cooling coil. And if we replace the temperature of the cooling coil ADP, which is given as the effective temperature, surface temperature of the coil. So BPF W2 minus W4, W1 minus W4. It is a specific humidity of the air at the outlet, specific humidity of the air at the inlet minus specific humidity of the air at the time of leaving the cooling coil. So H2 minus H4, your H1 minus H4. So actually the cooling and dehumidification takes place. Process follows the path as shown by dotted curve in figure 18 means here this path. Figure. This is a dotted curve here. This is this. This is the dotted curve from 1 to 2. But for the circulation of psychrometric properties, only the endpoints are important. Thus, the cooling artificial process shown by line 1 to 2 may be assumed to have followed a path 1 to A and A to 2. And we see that the total heat removed from the air during the cooling and diffusion processes Q H2 minus H1 minus H2, H1 H1 minus H4, HA minus HA minus H2 plus latent heat and vapor due to concentration of vapor of the vapor of the reduced moisture content W1 minus W2, LHSH, HA minus H2, sensible heat removed. We know that sensible heat factor is sensible heat divided by total heat. The sensible heat divided by total heat plus latent heat, HA plus minus H2 to H1 minus H2. So the total heat removed from the air during the cooling is Q H1 minus H1. H1 was the initial, H2 was the final here. H1 minus HA plus HA minus H2. HA H2, that is the latent heat and sensible heat. HR minus H2 latent heat is equal to the concentration of the reduced moisture content W minus H2 to 2. HR minus H2, the sensible heat that SFH is a sensible heat divided by total heat, SH divided by LH multiplied by SH, H2 minus H2, H1 minus H2. Now the line 1,4, that is the line joining the point of in 29 is shown as sensible heat factor line. Here's the line joining 1 to 2. Line joining where is sensible heat factor. 1 to 4 from here. Let us go through some problems. In a cooling temperature, a cooling application, moisture enters the refrigeration coil at a rate of 100 kg per kg of dry air per minute at 35 degrees centigrade, 50 kg relative, 50% relative humidity. The apparatus dew point of the coil is 5 degrees centigrade and bypass factor is 15 degrees centigrade, 0.15. Therefore, the outlet state of moisture and cooling capacity of coil is given as TR. Now, given MA is equal to 100 kilometer per kg per minute, and driver temperature is 35 degrees centigrade, phi 1 50 degree right transfer, ADP 5 degrees centigrade, TPF 0.15. Now, MA 100 kg per minute, PD1 35 degree, that is 35 degree here, plotted here, and phi 1 50 degree, which is to be supposed to be here, ADP 5 degrees, dew point temperature additional dew point 5 degrees centigrade report comes from here, and BPF is 0.15. So TT1, TT2, and phi 2 temperature and relative humidity of air leaving the cooling coil. TT2 temperature and relative humidity of the air leaving the cooling coil. First of all, mark the initial condition of air, that is 35 degrees centigrade dry bulb temperature and 30 degrees 50 degrees centigrade relative humidity of the psychrometric chart at point 1. Initial 35 degrees we have plotted here, and 50 degrees centigrade phi 1 relative humidity we have plotted here in the psychrometric chart. Now, the psychrometric chart will find that the dew point temperature of the air entering at point 1 PDP1 is 23 degrees centigrade. At point 1 is 23 degrees centigrade. So if you draw a line from here, it will touch the wet bulb temperature line, and that is equal to TDP1. That is 23 degrees centigrade. Since the coil or apparatus dew point is less than the dew point in the entering air, therefore this is a process of cooling and diffusion. We know. So that DP bypass result TDP minus TD4 divided by PD1 minus TD4. The bypass factor TD2 minus TD4, TD1 minus TD4. The TD2 minus ADP divided by TD1 minus ADP. Where ADP no, this is his factor, and ADP apparatus dew point, apparatus dew point. The effective surface temperature of the coil is known as apparatus dew point. Thus, ADP is the apparatus dew point, that is equal to 5 degrees centigrade, which is given by us. Apparatus dew point ADP, which is also available from this point. Now, put the value of ADP is 5 and 5 degrees and 5 degrees centigrade, and TD1, the dew point temperature entered 35 degrees centigrade, and put the bypass factor as 0.15. So after calculation, we'll get 0.15 into 32, means it is become 32. After you have it goes here, and thus upper dew point at the point 2 and the point of leaving is 0.15 into 30 plus 5 is 9.5 degrees centigrade. So scientific chart, we find that the relative humidity of the corresponding to the dry bulb temperature is 955 is on the line. On the line 1,4 is phi 2, the 98%. Now, cooling capacity of the coil, the resulting condition of the air
coming out of the coil is shown 3.2. Now on the line timing the point 1 and 4 and figure. The line 1, 4 represent the cooling and humidification process, which may be assumed to have followed part 1 to 4 and 8, 1 to A and A to 2. From the psychrometric chart, we find that enthalpy or entering at point 1 is 81 kilojoule per kg, enthalpy at point 2, 28 kilojoule per kg. Now the cooling capacity of the coil MA, H1 minus H2, MA is the mass of the air flowing in, multiplied by H1, H1 is 85 and H2 is 28. This becomes 5300 kilojoule per kg. So 5300 kilojoule square of 210, 25.24 into kilo TR. So what is clear here from this formula, the psychrometric chart, we can get the enthalpy. From the psychrometric chart, we got 1, and at the enthalpy at the point 2, both we have got the cooling capacity of the coil. We know the mass which is given 100 kg per second, and multiplied with the enthalpy change, which is equal to 5300 kilojoule per minute divided by 60 and divided by 210. It's 25.25 is the tonnage capacity per metric ton. So this is defined, you will get 25.24 to metric tonnage of refrigerant. Now, next problem is (39.6 meter cube per minute of mixture of recirculated room air and outdoor air. Recirculated room air and outdoor air enters a cooling coil at 31 degree dry bulb temperature and at 18.5 degree wet bulb temperature. The effective surface temperature of the coil is 4.4. The surface area of the coil is such that it would give 12.5 kg per of refrigerant with the given entering air state. Determination by the dry and wet bulb temperature of the air leaving the coil and the bypass factor. Now, the effective surface temperature of the coil is 4.4. Surface area of the coil is such as give 12.4 kilojoule of refrigeration with the giving entering air rate. Sometimes the dry and wet bulb temperature of the air leaving the coil and the bypass factor is given as V1 39.6 is the bypass factor. Determined by the dry and wet bulb temperature of the air leaving the coil and the bypass factor. So V1 temperature of incoming air dry bulb and temperature of the outgoing air dry bulb 2 is given as and dew point temperature is TD4. The apparatus dew point temperature ADP apparatus dew point temperature dew point temperature, it is given as 4.4 Q 12.5 kilowatt, that is equal to 12.5 kilojoule per second, 12.5 to 60 kilojoule per minute. So dry and well bulb temperature of the air leaving the coil. The TD2 and TD2 dry and well bulb of the temperature leaving the coil. First, mark the initial condition coil at 31 dry bulb temperature, this is here, and 18.5 wet bulb temperature, that is here. And from the cyclic chart, now the effective surface temperature of the is 4.4 here, and from the cyclic chart, H1 is given as 52.5. Enthalpy at the point 4, the dry bulb temperature is as low as 17.4 here. The specific humidity at the point 1 is given as W1 here, and specific at the point 4 is W4 here. Specific volume at point 1 is where on the also from the chart is available VS1 0.872 cubic meter. So mass flow rate of dry pair at point 1 is V1 by VS1, the specific volume. So mass flow will be 39, velocity divided by specific volume is equal to 44.41 kilojoule per minute. Now, the cooling capacity of the coil is supposed to be given as H2 minus H1, or Q divided by MA, or Q is given as 12.5 into 60 divided by 44.4, that is 16.9 kilojoule per kg. So H2, H1 minus H2, and H1 is available from the start 52, and this H2 is equal to 34.61. The equation for the condition of the line 1 to 4 means 1 to 4, W2 minus W4, W1 minus W4 is H2 minus H4, H1 minus H4. They put the individual values of W4 and W1 and H1, H4, we get W2. This is the specific enthalpy at W2 here, and 0.00677. Now plot the point to cyclonic charge as the enthalpy H2 of dry air and specific enthalpy, which both are given, and at point 2 will get dry valve temperature is equal to 18.5 to drop a particle, and wet valve temperature is equal to 12.5. So by the bypass factor H1, H4, H1, H4, both are available. H1, H2, H4, H1, H4. H1 and H4 is available from chart, and the 17.4 is the enthalpy available at the point 4. That is the apparatus dry valve temperature. So if you put this value, you get ppf is equal to 0.1546 kilojoule per kg. Okay, so much for the day. End the class.